I've taught biochemistry for over a decade now, and the concept I found that confuses students more than anything else is free energy. And the problem with this, of course, is that free energy is also one of the most essential things to understand if you're going to make sense of biochemistry. So in this video, I'd like to unpack free energy from a perspective maybe you haven't thought of before, and that is free energy as a bet. So let's get into it. So when we're thinking about biological systems, we often encounter a free energy. So for example, if we're imagining a protein that's in equilibrium between a folded form and some kind of unfolded form, we could describe this equilibrium using a free energy. We might also encounter it in, say, metabolism, if we're thinking about, well, what is the amount of energy that a cell can extract or use out of, say, glucose respiration or a combustion reaction, as I've written it here. How do we get energy out of that? And so there's this thing looming, this delta G, which looms over everything that we think about. But if you start trying to poke around online, maybe look at Wikipedia, the information is correct, but maybe difficult. So I'm going to this is the Wikipedia definition, that it's a thermodynamic potential that can be used to calculate the maximum amount of work other than pressure volume work that may be performed by a thermodynamically closed system at constant temperature and pressure. And this is correct. And thermodynamics, one of the things that's important about thermodynamics is rigor. But in this case, I think what we're actually doing is by being rigorous, we're losing clarity. We're losing what in the world this free energy thing is telling us. And what I'd like to argue, and I think that for a student particularly, that maybe the best way to think about free energy is simply as a bet. And so let's unpack that a little bit. So let's come up with a real model to show, or a real system to think about. So we're going to imagine an alpha helix, which can be in a folded alpha helical form, in some kind of unfolded form. Even if you don't know much about proteins, hopefully you can recognize that the thing on the left is sort of more ordered than the thing on the right. So there's some transition between two states here. Now we draw these as reactions, but really that's an abstraction. So what I'd like to actually think about is what could happen if we looked into, say, a test tube that has a bunch of copies of this peptide in it. What we would observe is that there are a bunch of peptides that are in the folded alpha helical form, and then some others that are in the unfolded form. And now I'm showing this frozen in time. If we advance time just a little bit, what we'd see is we'd start seeing transitions between different states, right? Some of the helices that are folded are unfolding, some of the ones that are unfolded are folding, etc. This process is happening just continuously. For organizational purposes, we sort of mentally slide these onto two sides of a reaction, right? We've got the helix side and we've got the unfolded side. And then we imagine the reaction is continuing to occur, right? So this helix folds. Now in our bookkeeping, we have to move it over to the helix side from the unfolded side. This unfolded molecule moves over to this helical molecule unfolds and moves to the unfolded side, right? So that's the process that's happening. If we're thinking about this as a reaction, we have to keep a couple of things in mind. The first is that it is random whether a particular molecule folds or unfolds, right? If we're just looking at one, it's going to be a random draw whether it's going to fold or unfold. And then finally, that biochemists always deal with populations, not individual molecules. So we are looking at a whole population of peptides that are going between these conformations. And if you think through these conditions, what this means is that we get to do statistics. Now, maybe you're like, oh no. And this is one of those cases where we're going to take something that's difficult for students to understand, and we're going to try to explain it using something else that students I've found struggle to understand. But it turns out this is one of the problems where statistical thinking actually makes your life easier, like seriously easier. So if you don't believe me, stick with me through this video, and hopefully by the end I'll have convinced you. Okay, so let's do some statistics. And the model that I'd like us to all have in our head is that free energy is a betting odds. Just I'm going to keep saying that, and then you can keep deciding if you believe me or not. So if we're going to do a statistical exercise, we have to use statistical objects. So statisticians are allowed to use coins, dice, cards, balls and urns. There's like a limited list you're allowed to use as a statistician. So we are going to use coins, and we're going to replace the unfolded molecule with the tails of a coin and the folded molecule with the heads. And then we're going to imagine a toy reaction that's visible that we can see sort of with our eyes rather than a computer. And so let's imagine we have a table that has 1,000 coins on it. We're going to imagine that there are our moves are going to be we pick up a coin and we toss it, we put it back on the table. Then we reach and we grab another coin randomly, we pick it up and we toss it and we put it back on the table. And we just do this over and over and over. So big table with 1,000 coins where we're flipping them one at a time. We're going to flip, do 5,000 flips and sort of watch what happens. All right. So let's start with making a prediction. Imagine that we start with 500 heads and 500 tails. What's going to happen to the number of heads and tails as we start flipping the coins? So what's going to happen, and then why is that going to happen? So this is one of those videos where it's really important, I think, for you to pause and think about things, not just sort of watch it as it goes. So I totally strongly recommend you pause the video and think about the answer to these questions before I show the next slide. So here, I'll give you a chance to find the pause button on whatever device you're using. You're pausing. Assuming you're unpausing, this is what's going to happen. So if the reaction starts with 500 tails and 500 heads and 500 tails, over time it will remain about 500, right? So the number of heads and tails is going to fluctuate. They're going to go up a little bit higher. You're going to get a few more heads and a few more tails, and it's going to go up and down over time. Okay. What's happening here? This reaction is at equilibrium. When we say equilibrium, this is what we mean. That the rate of reactant to product and the rate of product to reactant is the same. Wow, the same. So the concentrations of products and reactants remain the same over time, right? So you're forming just as much product as you are losing. Now, really critically important point is that in this simulation and in chemical systems, the individual molecules continue to react. This equilibrium condition is not an endpoint where we've exhausted something, we've gone to completion or something. The system is not frozen. You're continually flipping back and forth. Heads are going to tails, tails are going to heads. In the helix example, helices are going to unfolded, unfolded are going to helix. Even though when we measure the concentrations of the products and reactants, they're not changing, we're still seeing reactions between the states. All right, so now let's make another prediction. What is this curve going to look like if we start with 999 heads and 1 tails? And why? So 999 heads, 1 tail on the table. We're going to start tossing it. What's going to happen and why? So again, pause. Okay, unpause. So what's it going to look like? If the reaction starts at 999 heads and 1 tail, over time it will, it will zoom up. It will equilibrate. What do I mean by that? Here's what I did. I ran, I guess I didn't say earlier, these are simulations that I'm running inside of a computer, effectively tossing coins. What we see here is it equilibrates, right? We start out with 999 heads, we start with 1 tails, and at the end we are at about 500 heads to 500 tails. The reaction has equilibrated. And at the end, we are in this equilibrium condition, right, where the rate of forming heads and tails is exactly opposite. But over here, we have a difference in the two rates. So why does the reaction behave this way? Well, at early time points, the number of heads is greater than the number of tails, which means on average, we'll see head to tail more often than tails to heads, right? We just have more heads around. If I just grab a coin off the table, the odds are it's going to be heads. I'm going to toss it, and then maybe I'm much more likely going to see a head to tail transition than say a tail to head. But after a long time, the number of heads about equals the number of tails, which means on average we'll see head to tails as often as tails to heads, right? If I just grab the population, the odds are I pick up a head or a tail with about the same frequency. And so when I start flipping that coin, I end up with the transitions at about the same frequency. We just saw a spontaneous reaction, right? We use this word in thermodynamics land like it's something special, but all that this, in a thermodynamics context, this is a thermodynamic process that occurs without the input of free energy from outside the system. We just saw something spontaneous, right? We started out with 999 heads and 1 tail, and wow, what do you know? We ended up with 500, and that will happen every single time, right? That is a predictable outcome because this reaction is in fact a spontaneous reaction. Okay, so let's do another prediction. In this case, I'd like you to imagine we're making a wager. Imagine that I have a lot more money than I actually have, and I'm going to $1,000 to you and everyone else who guesses that what the next transition will be. So you're basically trying to guess whether you're going to see a head to tails next or a tails to heads. I give you the option that you could guess either after 2 tosses, so over here, or after 5,000 tosses over here. Which would you take and why? Would you rather take the bet on over here or over here? I guess it's probably under me. Over here or over here? On the left or on the right? So this is a really good point. Pause. If you have somebody next to you, this is a good chance to get into an argument. So pause. All right, coming back from the pause. When I do this in actual classrooms, there's often a pretty robust debate about this between people that say you should make it at a specific place and then a group that says that doesn't matter where you make it. Anywhere you make the bet, the odds are still 50-50. And it turns out that the correct answer is that you would rather take it after 2 tosses, that you strongly prefer that. And the reason for that is because after 2 tosses, your odds of a heads to tails is much, much greater than your tails to heads, right? So if you wanted to, get $1,000, you'd get $1,000 much more often over here if you bet head to tails than you would over here. See, down here, your odds are basically 50-50. If I, bet heads to tails, I'll win the money half the time. If I bet tails to heads, I'll win half the money half the time. But if I'm over here, if I bet head to tails, I'll win it most of the time. So it's always better to make make the bet over here early in the transition. Okay, so hopefully that makes sense. This is it. This is all that free energy is. Free energy is a measure of how confident I would be if I had to bet whether the next event is forward or reverse. You could write this as the delta G equals minus RT log the probability of a forward reaction or the probability of a reverse. I like thinking about it is you imagine you froze in time, and you're looking at your molecular system, and you're just making a bet. What's the next thing I will see, forward or reverse? Helix to unfolded, unfolded to helix, tail to heads, heads to tails. Okay. And when we put it in these frames, hopefully the scale you've probably encountered in the past starts to mean something. So let's think about delta G equals 0. This is when the forward and reverse probabilities are the same. Your delta G is 0, and so you have odds favoring neither. Both events are going to happen. You're going to see forward reactions and reverse reactions. It's just you don't know which is going to occur, right? They're equally probable. If you go way up here to the delta G way less than 0, on that side of the scale, that's saying that the odds strongly favor the forward reaction. It's a good bet to say, I think the reaction is going to go forward before it'll go backwards. And then down here, it's the opposite, right? That if your delta G is much, much greater than 0, that's saying the odds strongly favor the reverse reaction over the forward reaction. And it turns out you can actually directly convert delta G into relative probability. So I wrote this expression up here. That was the one that I showed before. The delta G equals minus RT log of probability forward over reverse. You do some log rearrangements and you get this. That's saying the ratio of the forward probability over the reverse probability is e to the minus delta G over RT. And then we can plot that. And that's what I'm plotting here. So on this axis, I've got delta G going from negative 20 to 0 here, and then from 0 to 20 here. And then on this axis, I'm plotting the ratio of the forward to reverse reaction. And this is plotting the ratio of, again, the forward to reverse. And hopefully what you can see here is that if you're at 0, this 0 point, you got 50-50 odds, right? That's just saying, I don't know whether it's going to go forward. I don't know if it's going to go backwards. The odds are 50-50. There's no bet that I could make better than 50-50. But as you move away from that, in this case towards the negative direction, what it's saying is that your odds of seeing a forward reaction before a reverse reaction are higher and higher, right? So the probability of seeing a forward reaction first is 7.5 to 1 here. Negative 10, it's 57 to 1. Negative 15, it's 425 to 1. Negative 20, it's 3,000 to 1. In fact, that's actually one of my milepost numbers that I keep in my mind, is that at physiological temperature, delta G of minus 20 corresponds to 3,000 to 1 odds of going forward. Minus 20, 3,000 to 1 odds of going forward. But this scale is, of course, symmetrical. And so the opposite is true. If I have a positive delta G, a delta G of plus 20, that doesn't mean the reaction isn't going to happen. It means that the odds of the reaction going forward are much lower than backwards, right? If I'm just sitting there looking at a pool of reactants and products together, and I'm trying to bet what the next reaction is going to see, I'm going to take 3,000 to 1 odds I'm going to see a backwards reaction rather than a forward reaction. And these are exponentials. which means the numbers get really, really big very, really fast. So if I have a delta G of minus 30, that's 180,000 to 1. Minus 50, it's whatever that is. I can't do 575 million to 1. Minus 100 is whatever that huge number is to 1. So part of the reason we take these logs or do delta G's is because these numbers become very difficult to work with just because they're so big. But keep in mind that really what this is encoding is just a relative probability of forward versus reverse. I think another useful way to think about delta G is as a measure of the distance away from equilibrium. So here in this reaction here, I'm at equilibrium over here. My delta G equals 0. And when I'm over here, my delta G is much, much less than 0. I define this reaction as going from heads to tails. So I've got an excess of the reactants. So I have a high probability of seeing heads to tails reactions. And so where I am on this scale, the delta G starts out very negative and gets more and more closer and closer to 0 as I proceed because I'm getting closer and closer to equilibrium. I had a graphic for that, but that's the equilibrium there. Right, I did it with a pen. I did it also here with slides. And so we can put that on this graph as well. So here I'm showing these odds. You could also just think about this as distance from equilibrium. If I'm at a delta G of 0, I'm at equilibrium. As I move away from that, I'm getting further and further from equilibrium. I'm getting more and more information to say which way the reaction is going to proceed. Okay, so here we got this expression, that delta G equals minus RT log of positive forward probability over the reverse. That's sort of, I think, the simplest, most central way to talk about free energy. There are other ways it's formulated. In fact, I'm going to have a couple of videos coming up here where I talk about other ways we write it, maybe to relate it more explicitly to chemical things like concentrations and rate constants. But this at its core, I think, is what the free energy is measuring. When we're at equilibrium, our delta G equals 0, meaning the odds favor neither forward nor reverse. When we're out of equilibrium and our delta G is less than 0, it says our odds are favoring forward reactions. And when we're out of equilibrium with our delta G greater than 0, it's saying that the odds favor the reverse. If you take nothing else away from this video, I would say view it as free energy is a bet. It is a bet on which way the reaction is going to go. And once you start thinking about it that way, I think many, many problems in biochemistry, many, many puzzling things about metabolism make a lot more sense. So, all right, that's what I got on this. Thank you so much for your time. Hope it was helpful, and I will see you later.